In this section of notes, we're going to look a little bit more at the idea of correlation. So we talked about describing a scatter plot, and we talked about direction, form, strength, unusual features. Correlation is specifically that strength piece of the description. So a couple things you should know is that we use the symbol R, and there will be a calculator piece shortly where you'll figure out how to find the R value. And your R value is always a number between +1 and -1. Oftentimes it's a decimal. If the R value is positive, that indicates a positive association, which means if you were to draw a line close to the points in your scatter plot, that it would have a positive slope. And if the R value was negative, then that means that it would have a negative slope or a negative association. And if the R value is close to 0, we say that it has a weak relationship. And the closer the R values are to 1 or -1, then the stronger that relationship is. Now these values, this is just a picture to kind of get you to start seeing what the different R values look like. So remember, if you could draw a negative sloped line through the data points, that's when the R value is negative. Or if you could draw a positive sloped line through it, that's when your R value is positive. Something to kind of keep note of here, if your R value is positive or -1, that's when we describe the relationship as being strong. If your R value is close to positive or -0.5, we'll say that it's moderate in strength. And if your R value is close to 0, that's when we'll say it's weak. For values in between these, like a 0.7 or something like that, for values in between, that's when you're going to use an ly word. So maybe if it was 0.7, you would say it is moderately strong or is relatively strong, something like that. So add an ly word to it to describe your strength. Now there is a formula to calculate R, and it involves taking all of the ordered pairs and splitting them into x values and y values, then finding the mean and the standard deviation of the x's, as well as the mean and the standard deviation of the y's, and then you take each individual pair, take the x value of the pair minus the mean of the x's divided by the standard deviation of the x's, do the same thing for the y's, multiply those together, and then do that for every coordinate, and you can kind of see this long formula here. The good news is that you're never going to do this by hand. This formula is on your formula sheet, but you're always going to find your R value from your calculator or maybe from some computer output, like a Minitab output, but you wouldn't ever be doing this by hand. So here is that formula for your R value on the formula sheet. Again, it's there. You won't really need to use it though. All right, there are a few things here to know about R. First, R is just the correlation, and it doesn't really matter when you look at your set of ordered pairs what the explanatory or the response variable is. So that means, like, if you were looking at a set of data and you are having trouble figuring out what you think should go on the x and y axis, in terms of the R, it really wouldn't matter. If you were to take a set of ordered pairs, plot them, calculate the R value, and then start over by switching the x and y coordinates. So the ordered pair, for example, 2, 4 would turn into the ordered pair 4, 2. You would actually get the exact same R value. Similarly, let's say your x-axis was a time measured in seconds, and then you changed it to a time measured in minutes, and then you calculated the R value for both, you would get the same R value. So it's not changed when you change units of measure. Similarly, R itself does not have a unit. That has to do with unit analysis that you might have done in chem class, where you make the fractions and you cross things out. What ends up happening in that formula, because there are fractions there, is that you end up canceling out any units. So R does not have a unit. And lastly, some things to think about here. You can't find a correlation for categorical data. It only works when both the x and the y values are quantitative. Also, remember that correlation is a specific type of association, and it's only for lines. So if your data shows a curved relationship, then you're going to use the word association. If your data looks like a line, then you're going to use the word correlation. And we say that the correlation is non-resistant. So just like mean and standard deviation were non-resistant, and we switched to using median and IQR if we had a distribution of data that had a skew or had outliers, the same thing's true here. R does not really work very well if your data has outliers. And then last, there are going to be some other things that we'll look at besides just the R value that's going to let us talk about and summarize our data. Now, just a few more cautions. You may have heard the saying that correlation does not equal causation. And here are some examples. This is kind of a fun website if you have some free time and you want to just do a quick Google search for spurious correlations. So spurious essentially just means that two things appear to be related and it's just like a coincidence. So here he has this whole website just filled with things that look very close to each other. So here, this one, we've got this R value of 0.94721. And with this data, people might try to argue that as cheese consumption increases, then people are more likely to die by getting tangled in their bed sheets. Or they might be able to say something like that as the divorce rate in Maine increases, that their consumption of margarine decreases. So these are things that appear to be related, but if you think about them for even a short amount of time, you know that they're not related. So these are examples of things called spurious, which again just means kind of like by coincidence. Now there's also something called a lurking variable, which is a little different. Lurking variables are a lot like confounding variables. It's just that we use them in two different scenarios. So confounding, you'll remember from back in chapter 4, confounding was when we had some third piece of information that impacted two other things in an experiment. Lurking is the exact same thing, but for when we have these two sets of data, we have X's and Y's, we have ordered pairs. So for example, there has been data that shows that as the consumption of hot chocolate increases, so does the rate of car accidents. Now, at first, that sounds a lot like these spurious outcomes because you know that it wouldn't make sense for car crashes to increase as people drink more hot chocolate. However, there is a lurking variable there. There's a third variable that would make both of those increase, which would be the weather. So if it's cold and icy and snowy, people are more likely to want to drink hot chocolate, and they're also more likely to get into a car accident. So a lurking variable is when you have a third variable that impacts the other two, making those other two look like they're related. Whereas spurious is where you can't really think of a third variable. It's just a coincidence. All right, don't forget to go through the calculator videos for this section and then try the practice problems before moving on.